All right, so here we go, going over the IMF comparison worksheet. Yes, here we go. So we're talking about intermolecular forces of attraction, and party people, we are talking about, okay, this idea of forces of attraction between molecules. These are molecular compounds. Okay, so you don't have to know the molecular formula. You don't have to be able to take the names and be able to make the shapes. The shapes have been given to you, okay? So that'd be another course to figure out how to actually write these structures. Okay, so what do we have here? We have these structures. Notice the molecular weight of them is about the same, and that's an indication that they have about the same number of electrons. And that kind of tells you that if they've got the same number of electrons, then they all have about the same probably effect of polarization for LDFs in terms of electron numbers. So if there's a difference in LDFs, it's going to be due to shape, probably. Okay, or definitely. All right, so let's get crazy and start in order. And so we're going to leave this up here, and what we're going to do is we're going to make some some understanding in terms of, or some comparisons, since is the comparison worksheet here. We're going to make some comparisons of the different intermolecular forces, and notice I have the boiling points written on the bottom here. So I'm going to go make some arrows and we'll have some fun doing that. So let's get started and let's talk about the first force that all molecules have, and that's LDF forces. Okay, so I'm going to make myself, let's go with blue for LDF, and let's do this. So looking at these four objects, I look at pentane. Pentane jumps out at me because I know that it's not polar. I can see that it has 0 dm, and that, of course, dm right there is nothing more than Debines or dipole moments. I'm sorry, so 0 dipole moment there. That probably should say dB, Debines, right across, and I can see I have a mistake there. It's dm, I should have Debines, and that's the dipole moments. Any case, that being said, I look at pentane as having the greatest of all, okay, of the LDF forces. And I know that because although all of these have about the same number of electrons, this elongated shape for pentane makes it more polarizable. Okay, and then looking down, okay, what would be another LDF that I think might be second place? And I'm going to say N-butanol is elongated too. So I'm going to draw one right here. Not that. I'm going to draw one right here. And I'm going to say that's second place. And how do I know? It's got a longer structure, just like pentane, all right, but not quite as long and not quite as polarizable. That oxygen at the end kind of locks that cloud a little bit. All right, now we got who's going to be second to last and last. Well, I'm looking at butanone here, and butanone here is going to be last, and there's a reason for that, and we're going to just draw a small arrow here. Butanone is last because it's got a more branch structure. When you have a branch structure, it's hard for that momentary dipoles to shift one way. The more branching you have, the more circular you are, it's hard to really make a partial negative charge by electron clouds moving. And so I would say that the propanoic acid is second to last because it's got a long shape, but not quite as long, all right, as the others. Okay, now let's talk about dipole forces. And of course, all molecules have LDF forces, but not all molecules have dipolar forces. So if we think about dipolar forces, okay, who is polar? Well, we can see pentane is clearly not polar, but we can see that butanone is the most polar, and that again should be dB for Debines, and this has the second most, I'm sorry, the propanoic acid is the second most polar, probably because of these two O's here. And this N-butanol is the third most polar of this group, and because it's got this long structure that kind of limits the polarity of this O here. As long as this gets here, it's harder for this O to make a big difference in this nonpolar region. So this is going to be the propanoic acid, of course, is that. So let's get the arrows in. And again, you don't have to ever look at molecules and say who is more polar than something else. You'll be given these dipole moments or these Debine values to do that. So let's go and put some more arrows in. And I'm going to make that a red for polar. And let's do that. So who is the greatest amount of polarity? Well, butanone. It's got that 2.76. And who is in second place? Well, 1.76. All I'm doing is just reading the, and I'll put that arrow second. And we know that N-butanol is polar. It's 1.6, so it's going to be in third place. Okay, and I'll put that there. It's just a relative scale, so how big the arrows are. Okay, and of course, pentane over here to the right doesn't get an arrow for dipolar forces. It doesn't have any. It just have LDS. But notice everyone's got LDFs. Everyone's got a cloud of electrons that can momentarily move. Okay, so H bonds. Now, H bonds is the third force, and if you're going to have H bonds, you're going to have LDFs because you have a cloud of electrons. Every molecule does, and you're going to have dipolar forces because you have to be polar in order to have H bonds because you have a difference in electronegativity of the atoms bonded. H bonding is a special case where you've got these electrodeficient H's. Yes, so we're looking for electron deficient H's, and I see one here, and I see another one here, and these are electron deficient H's because, as I pointed out before, electron deficient H's are a scenario, okay, where we have a electronegative atom like oxygen pulling electrons so much that the remaining proton, that's right, there's just a proton in hydrogen, its electrons are pulled so far away that essentially you've got this very small but very positive, okay, proton that's going to be really extremely positive, almost as strong as a +1 in an ionic bond. But that only occurs when you have these very electronegative atoms that pull these electrons, and as you should know, we have Fon in H bonding, which means an H has to be attached to a nitrogen, oxygen, or a fluorine in order to create that scenario where you really have a really high positive H. And this high positive H, okay, will be able to attract the negative part of the oxygen in the same molecule. So party people, okay, we have two and it's important to understand we have two molecules here that can undergo H bonding, and one of them, okay, two of them can undergo H bonding, and one's a little bit better because of less stuff in the way, or this alkyl group here. But in any case, more importantly, it's hard to discern who is going to be stronger H bonding, so we're going to put those arrows together. But I want you to understand, really important, that when we talk about boiling points that we have down here, okay, we're talking about how well propanoic acid will attract itself. Don't get lost in this. How will N-butanol attract itself? Well, it attract itself with LDFs because it has what? The cloud of electrons. It's polar, which means it has a negative and positive end, so it will attract itself that way. And then it also will H bond, meaning this positive H of N-butanol will attract the O of another N-butanol. Don't forget that. So in any case, let's go back and let's put some arrows in. And I'll make my arrows, I don't know, whatever color this is. And I don't know who's better at H bonding. I'm just going to put these arrows in. Let's put these arrows in, and they're about the same. You know, again, probably easy to H bond these O's sticking out, so maybe there's a little better here. This O is going to have a tough time H bonding with this big alkyl group in the way, but I'm going to leave them there. If anything else, they're the same. Okay. All right. So we've got our forces of attraction, and we have evaluated them. Okay, and now we're going to make some sense to what the boiling point means. All right, so, oops, let's go back. I just erased it. So let's put another one there. Bad Grutsky. That does not have H bonding. Okay, so we're going to do that. And I didn't erase anything, so let's continue on in this madness. All right, so let's get this. All right, and let's talk about the bond. Let's talk about the bonding. Okay, so we have the lowest boiling point. What are boiling points? Boiling points are where the energy needed to what? It's the temperature at which the vapor pressure upward from a liquid evaporating equals the atmospheric pushing down. Bottom line is, how much energy, temperature-wise, do you think the temperature gives us an indication of energy, but how much a lower temperature or greater temperature in the case of propanoic acid, the greater the boiling point, the greater the energy it takes to separate the what? The molecules into the gas phase. So party people, look at propanoic acid. It's got 3 of the forces. It's got all 3. So because it has more, all three, cumulatively speaking, it's going to have the highest boiling point. Well, wait a minute. I mean, N-butanol has got all three as well. So why would propanoic acid have a higher boiling point? Here's an AP question. Compare and contrast the boiling points of butanol, N-butanol, and propanoic acid using their intermolecular forces. Well, if you just said that, okay, they all have hydrogen bonding, you need to talk about specifically what's happening. They both have LDFs. They both have dipolar forces. They both have H bonding. What's the difference? The difference, it appears to me, okay, is that the dipole moment of propanoic acid is great enough, okay, to separate it in terms of its overall attractive forces for itself. So this dipole moment being so much more what? Polar, it attracts itself so much more that increase, when you comparatively speaking, the dipolar force in propanoic acid must be the difference. Now, if you look here, N-butanol has probably greater LDF forces, okay, but the greater difference in the dipolar force here is probably what's happening, what's going on in terms of the difference. Definitely is. So you'd have to say in your AP understanding is that propanoic acid and N-butanol have the same number and type of intermolecular forces of attraction, but propanoic acid has greater dipolar forces as noted by its what? It's 1.76 to binds or dipole moments. Now let's talk about butanone and pentane. Why is pentane the lowest? Well, it only has what? One type of force, which is the weakest of all three, although they can be significant enough to be solids. This only has LDFs, okay? So if I was to compare and contrast butanone with pentane, well, why is pentane so much lower? Or why is butanone have a much higher boiling point? Why does it take more energy or a higher temperature to separate the liquids? These butanone must have high attractive forces. Well, their answer is, and if you just said, well, butanone has dipolar forces and pentane doesn't, you would get it wrong. You must say that pentane has LDF forces, as does butanone. But butanone has an additional force of a what? Dipolar force that pentane does not. And that additional force will give it a greater collective intermolecular force of attraction, meaning these molecules will stick together stronger and therefore take more energy to separate. And why does N-butanol and propanoic acid have higher boiling points? Okay, why is these guys higher than the ones to the right? Because to the ones to the right, butanone and pentane, these guys only have 1 and 2 forces of attraction collectively. So it isn't that the what? H bonding is the strong attractive force. It is, but it's the cumulative effect, meaning to have H bonding, you must have dipolar and LDFs. And so having the cumulative effect of what? All three of these forces, okay, makes for you to have a much higher boiling point. You must mention that. Okay, let's go rank as we make a mess of this. And I have a key posted that's much cleaner than this if you want to get there. But let's go talk about miscibility in water, solubility in water. Now, solubility in water is important to talk about. And I make sure you can see this because sometimes I talk and I don't realize that you can't see. So solubility in water. Okay, well, we're going to rank them. And now when you talk about solubility in water, in order to dissolve in water, we talk about like dissolves like. Well, we know that water is polar and it likes to dissolve polar, but that's really not a great way to talk about it. If things dissolve in polar, we say if things dissolve in water, we say they're polar. And the reason why they're polar is that they share similar what? Similar attractive forces. Now, water, if you don't know, okay, has a cloud of electrons, so it's going to have LDF forces. It's polar. It's got a partial negative and a partial positive, so it has dipolar forces. And party people, it has H bonding because it has electron deficient H's. So what we're saying here is that if something's going to dissolve in water, it's going to have the most similar attractive forces, so that water can what? Break its bond or its attractive forces with itself, not bonds, and allow other molecules to get in the way and basically homogeneously dissolve them. Well, look at your choices, and let's clean this up here, okay, because I have a mess. Look at what we have here, okay? Well, propanoic acid and N-butanol, my friends in chemistry, okay, have the most similar forces. So we're probably going to say that those two are definitely miscible. All right. So how do I know which one is the best? Well, my guess is the one that is the most polar, okay, is going to be able to H bond better. Now, water has two electron deficient H's over here, right? And we see that there's one electron deficient H, but there's two O's for it to what? To attract to. So that's going to make me think that this one gets a number 1. It has similar intermolecular forces of water, and it's the most polar. Okay, if you don't remember, it's got the highest Debye value. Okay, so that's why I'm going to go with that. I'm going to make this number 2, and the reason behind that is it has similar intermolecular forces as water. It's not as polar, so it's not going to attract water as much. Remember, its Debye value is not quite as high. Okay, and then the next one is, well, pentane only has what? LDF forces. So I'm going to make this 4. It has the least, okay, similarity in intermolecular forces as water. So actually, it will not actually dissolve. Okay, so there we go. And then 3 is butanone. Some people will say, whoa, it doesn't have H bonding with itself. How can it dissolve in water? These guys will dissolve. This one won't. Why would this guy dissolve? Well, party people, okay, the reason why it's going to dissolve is because the biggest thing, although it does not H bond with itself, hello, it can H bond with water. And this is an important difference here. This little negative, partial negative, is going to attract this H, who is a partial positive. Okay? And so these partial positives of water can interact with this O. So water can H bond with this O. Even though this butanone does not H bond with itself, it can H bond with it because it has a very electronegative O. All right? So we would say that it will dissolve in water, and that's important you get that, but not quite as well as these guys because, well, yeah, that's a great question. I look at this better, okay, boy, it's really, really polar, okay, but because this can H bond with itself, boy, if I'm thinking about this, okay, I'm probably going to switch this because of the great polarity here. So we can definitely have an argument between these two here. And of course, this wouldn't be on a test, but I'm just kind of going over this, looking to see how polar butanone is and how, you know, this being so polar will attract water so much and water will H bond. I'm kind of thinking that this should be the 2 and this would be the 3. And we can have that discussion, but I'm going to say because of the polarity. Even though it doesn't H bond with itself, okay, because of it's so polar, it can definitely H bond with water. I'm going to change that. And I know my key I just posted has the opposite, but hey, I keep thinking, keep going. So explanations we kind of went over, okay? The bottom line for the highest boiling point for propanoic acid, it's due to having 3 intermolecular forces, LDF and dipolar and H bonds. This molecule has the highest dipole moment, okay? It's the most, well, is it not the most polar? It's the most polar of the 2 that have the what? The same attractive forces for themselves. So explaining this, again, we kind of went over that. So I guess I should continue on the back page. Again, if you want to read these explanations that I have written, check my key out on my website. Okay, so bringing back table H here. And table H that we've talked about is a table we have in our what? In our Regents level. And the reason I'm bringing it back is I want you to understand vapor pressure. Okay, vapor pressure, of course, is the force due to liquid molecules doing what? Escaping each other's intermolecular forces of attraction, getting to the surface and becoming a gas and flying up. And as we add more energy, okay, to a container that has a liquid, more of these molecules can overcome their attractive forces, get to the surface, and become a gas. All right? So as the temperature increases, vapor pressure increases for liquids. But if you notice, some liquids evaporate better than others. Hey, propanone has a much, much steeper slope. Well, why? It must have what? Weaker intermolecular force of attraction. And these liquids, or these molecules, do what? They essentially resist evaporating because they have a lower vapor pressure. Now, what's boiling point? Well, you should know, party people, boiling, okay, is when the vapor pressured upward equals a pressure pushing down. And since we're talking about standard pressure, okay, we're going to put some arrows in here, all right, and we're going to look at where the vapor pressure upward equals the atmospheric pressure. So we're going to come down, and we're going to get, that's a boiling point. Oops, it's about 56. And we've got this one. It's a little less than that. Oops, we can do this, maybe. And it's a little less, like 76. All right, and then another one. This is dead on 100, as we should know, because Andy Celsius made his thermometer in Celsius based on that, so of course it will come out that way. Oh, Christmas. And if you're watching this in Christmas time, I guess you're right. And then, of course, we have ethanoic acid, otherwise known as vinegar, or vinegar, yeah. Where we live, they call it vinegar. It's kind of a weird thing. Okay, so if I can do this, there we go. That's about 117. So the values we get, okay, for the boiling points, oh, Christmas, I lost some things here. So we've got this at 100 and another one at 117. Okay, all right. So if we write that in, and I keep doing that, right? Yeah, I'm being tall. One more time. Trying to figure out this new program I'm using for that. All right, cool. Now, I'm going to go and write in these values. This is about 56 for the propanone. For the ethanol, okay, this is 74-ish degrees Celsius. That's the boiling points. 100 degrees Celsius, Andy Celsius made it that way. And this is about 117 degrees Celsius for ethanoic acid. Of course, this is water. Okay, so let's get to this. All right, normal boiling points. Let's write them in. Propanone, 56 degrees Celsius. Ethanol, 75. Well, I guess 74 degrees Celsius. Water is 100 degrees Celsius. And ethanoic acid is 117. These are normal boiling points. Okay, so now once we have that, and of course these are the what? These are the compounds that are in your table right there. So let's make some generalizations about their LDFs. Okay, looking at this, okay, I can see that unlike the first page where I had the number of electrons were the same, we have a lot more electrons, okay, that are different here, okay. So if I look at my molecule with the greatest number of electrons, I'm looking over here at ethanoic acid. So I'm going to say that it probably has the greatest, okay, greatest LDF forces. It's got the most polarizability. Okay, it's kind of a long shape compared to the others, and it has a lot more electrons with those 2 oxygens. Okay, so we're going to go with this blue color, and so we're going to say this has a pretty high LDF. Okay, we're going to say water has the least LDFs. Now, why? It has the least amount of what? Is the least amount of what? Least amount of electrons, okay, as I try to move that and stall, okay, so LDFs, maybe. Okay, now we've got this ethanol here, okay, this ethanol to the left, it has what? Well, it's has a long shape in 1O, and I compare it to the propanone, who is more circular, it's got to be greater than the propanone. So I'm going to draw an LDF here, and I think that's going to be greater than the water, who is more circular. Not so much as this is the same, ethanoic acid is the same shape as ethanol, except there's more electrons. So that's why I did that there. And then, of course, the LDFs for propanone, because of its what? Circular shape compared to ethanol, okay, I'm going to say that it's lower, but greater than water. Okay. And again, just for fun, okay? Dipolar forces. Well, we have the dibynes. Now I have it right up there. And let's change this to red. Who is the most polar? Well, that's just given to us. Okay, clearly the one that's most polar is water. Okay, so water has the greatest dipolar forces. Who is, well, it's in second place. The one that's the greatest, the most polar, okay, is the propanone. So it has to be higher. And all I'm doing is what? Just using the values given to me in the dipole moments above. All right, and of course, to evaluate ethanol, it's got this alkyl group, 2 C's and an O, so that kind of limits it, but 1.68 is lower than everybody else. So make another point here. So that's going to go here, and this arrow here for dipolar forces is going to go a little less, and I think I have them relatively good there. Now, where are my electron deficient H's? Who's got electron deficient H's? Who's got electron deficient H's? Water does. Water does. Water does. This guy does. This guy does. Ah, so we've got 3 of them that can do that. So party people, let's draw that in. And we're going to make a different color. And we have H bonds. Hard to evaluate who has stronger H bonds. We're just going to write it in. And we have this. Delete and H bonds. All right. So now let's talk about how we can talk about why the boiling points are what they are, which of course would be inversely related to its what? To its vapor pressure. Okay, because that's what kind of what I went over here in this one. Okay, so any case, look at propanone. That kind of jumps out to me. It has the what? Least number of intermolecular forces. So therefore, it has the lowest what? The lowest boiling point, which means it evaporates easier because these molecules attract themselves not as strongly as the ones that have what? 3 forces. Now, when I compare these 3, especially on table H, okay, when I compare these 3, and I'm going to make sure that I can see what we're doing here. When I compare these 3, okay, up here, ethanoic acid has the what kind of vapor pressure? The lowest. It really, why would that be? Why this has the highest boiling point? Higher the boiling point, the lower the vapor pressure. You're holding together. So why? Well, if you look at it, it's got a pretty high what? Dipole moment. Okay, but more importantly, it's got this area here. It's got a huge what? Cloud of electrons because it has the most electrons. So here's an AP question. Explain why ethanoic acid, as compared to water, has a higher boiling point. And you would say, and this is important, when you do these kinds of comparisons, you must talk with both of them. Water and ethanoic both have LDFs, dipolar forces, and H bonds. They have the same number and type of intermolecular forces. However, ethanoic acid has a greater LDF force as compared to water because it is more, I'll write this subtly, polarizable. Why? Not so much the shape. Well, maybe this is circular, this is more elongated, but more importantly, there is more electrons in this electron cloud than this electron cloud, and you can count them. Carbon is 12. Carbon is atomic number 6. That equals the number of electrons. So 6 plus 6 is 12, plus what? 8 plus 8, and you can do that compared to the number here. And clearly, this cloud is richer, and that's what gives it. That's what gives it to have a greater boiling point. So they have the same forces, and they have similar what? Dipolar forces. What's different is the what? Right there is the LDFs. Okay. Now, why is ethanol so much lower compared? Because it has a substantial LDF force, but it's not quite as polar. Okay, so the lower dipolar force compared to the other, okay, offsets that. All right, so I hope that helps to look at this a different way. But when you talk about the strength of boiling, talk about the amount of boiling point, think about how much energy it takes to separate them. And if something boils at a low temperature, what does that mean? Like propanone we just did right here, okay, has the weakest attractive forces. Why? Because it separates these, and why? Because its vapor pressure goes up faster, and when its vapor pressure hits the atmospheric pressure, it's going to do it faster than the others and have a lower boiling point. Okay, so vapor pressure. So we can talk about vapor pressure. We can talk about boiling points. We know these are inversely related. Higher the boiling point, okay, lower the ability to create vapors because you're sticking together. And what else? Well, higher the boiling point, like ethanoic acid, like we just talked about, 117 compared to the rest of them, the lower the vapor pressure because it has the highest strength of intermolecular forces of attractions. All right, hope that helped.